Hi everyone, I'm Mike. Tap, is this thing on? Okay, looks like you can see me. This is actually my first time streaming on PapersWeLove and in general, so this is a pretty exciting experience for me. As Dave was kind enough to introduce me to, at least introduce me as, I'm a student at the University of Illinois in their online program. I'm currently studying I actually just finished a class in advanced distributed systems, which was a lot of fun. We ended up reading a lot of classes or a lot of different papers over the course of the semester, and this one turned out to be my favorite. I don't know about you guys, but I started with CAP theorem, which said the only kind of network partition there is one where the nodes are just lost from the network and there's a complete divide. And this paper showed me that that life is a lot more interesting. So for this, I started presenting. I unfortunately was not smart enough to leave myself a space on all the slides to show me, to leave my face on the slides. So I will disappear in a moment and we'll start talking. So PapersWeLove plural, there's more than one today. Starting off with CAP theorem, which I learned today is actually, CAP theorem did not start off as a paper. It started off a conjecture, and then the first paper actually proved the conjecture to be correct. Then we're going to talk into like what a partial network failure or partial network partition looks like inside of a data center. We're going to see how that looks, or what happens to Raft, which is a consensus protocol during a partial network failure. And then we're going to talk about two papers, three of the same authors for both of them, diving into different network partitioning failures, and then a solution towards the partition network failures for the partial network partition. I'm going to mess that up more than once. I'm going to apologize in advance for that. All right, so we're going to start with CAP theorem. So I'm guessing many of you already know. Oh, by the way, feel free, I'm paying attention to the stream chat. Feel free to ask any questions in the chat or hold questions to the end. I will check in between papers and every now and again to see if you guys have any questions for me. All right, so let's see. CAP theorem, as a reminder or as a refresh, is basically it proves that you can your distributed system can be internally consistent and it can be available and it can support network partition tolerance, but not all three at the same time. So if your distributed system is consistent, that means it doesn't matter which node your client asks questions of. It's always going to get the exact same responses to its inquiries. Available means that no matter what happens at any given time, the system is up and is available to answer questions. And then partition tolerance means that if the network partitions or there's a split and nodes can't talk to each other, your distributed system will continue to work. And often is that the theorem proves that you can't do all three, which often means, or gets reduced to, pick any two. A system that's both consistent and available is generally on one node. Think of SQLite, which is a file that contains your database on one node. There is no network, therefore it's not network. Has no tolerance towards network partitions. A consistent and partition tolerant system will say, all right, I will always make sure my system is internally consistent. And if something goes wrong, I just will stop being available until we can figure out what the problem is, generally with the network partitions. And then available means, all right, if there's network partition, if you ask one side of the partition for a question, you might get a different answer from the other side. So those are the types of things that you worry about if you're focusing on availability and partition tolerance. It means that, yes, your system will continue to work, your clients continue to ask questions, but they might not always get the correct answers every time. Now, the core assumption here, as I alluded to before, when a network is partitioned, all messages sent from nodes in one component of the network of the partition to nodes of the other component are lost. Meaning, if there are two nodes, A and B, and they're on opposite sides of the partition, there is no node C that I can send messages to that can see both sides. And we'll get into that, and we'll get into why that's not completely a fair. You don't want to stop thinking there about network partitions. So we'll pause for questions. No questions yet, so I'll continue on. So a scalable commodity data center network architecture was published in about 2008. This is more or less state of the art for data centers or network setups at the time for inside of a data center. The main reason is because it's cheap. the goals, the benefits of this is rather than buying a very expensive switch from Cisco that would allow you to connect all these 16 machines together, you could add 12 different switches arranged in this way, so you get some redundancy in your network, and also and it's also a lot cheaper to do it this way because each of these individual nodes would be a lot cheaper, or switches would be a lot cheaper than one big switch connecting them all together. Now, I bring this up because we're going to talk about what a complete network partition looks like, which, as you can see here, if that one router dies, you can see that those two machines it's connected to are completely disconnected from the rest of the network. So that's the kind of network partition we all know and love. Any packets going towards those systems get lost. Any packets leaving those systems get lost. Then they are completely cut off from the rest of the world. However, in a partial network partition, we get into an interesting case where yellow, blue, and red can all talk to each other, and green and red can talk to each other, but blue and yellow can't talk to green. And rather than make you guys walk through all those through your lines yourselves, I will just point this out for you. First, we have here any packets coming through the blue network can follow these routes to get to yellow and red. If you're coming from the yellow network, you follow these routes to get from yellow to blue and red. And if you're following green, you can go to red, but you can't make it to blue or yellow. And all attempts end up dying on that. But red can go in every direction. Red can talk to everyone. Now, so what kind of things that can run into this situation? First, you saw switch failures. We talked about that. We have connectivity loss. If someone chews through a wire. If your network card stops working. Some certain software failures, your software will stop. That's actually trying to route packets will actually do the wrong thing. Your network can be misconfigured. Your firewall can be misconfigured, or you could be in the middle of a network upgrade, and how you upgrade your network might end you in a place where you end up with a partial network. Your network's partially partitioned. Now, in the parlance of the paper we're studying on partial network partitions, we talk about this as slide 1, slide 2, and the bridge. And the bridge of the nodes are the ones that can talk to everyone else. And then your network partition is partitioned into side 1 and side 2, potentially more sides, but for the purpose of the paper, where this is your base idea. No questions yet, so we'll go into a case study on Raft and how Raft handles partial network failures. I won't go into how the Raft protocol works, but I do want to give a high-level just reminder. So you've got a leader. So Raft is a consensus protocol. We're trying to decide who's the leader of any a set of systems. We effectively, leader performs writes. Those writes get replicated out to the followers. And so you can ask for the current information from any individual follower as a reader. And then if you want to perform a write, you need to update the leader. The leader will send out notifications to at least 3 followers to reach quorum, and then be able to and then commit the write once it's confirmed that all 3 nodes have been all 3 writes have succeeded. So if we have a network partition, we're now in a place where the leader no longer has access to 3 nodes to perform any writes, and the followers have lost access, or 3 of the 4 followers have lost access to their leader. What this ends up happening is the leader can no longer perform any operations because it doesn't have consensus. It can send updates to 1 follower, but not 2. It can't reach consensus. And so on the other side of the network partition recognizes that they lost access to their leader. They start a new election. A new leader gets elected, and operations on the bottom left side of the partition will proceed as normal, while on the top right side, basically the cluster or those 2 nodes are no longer able to proceed. Now, eventually, the network partition heals itself, and this means that the uncommitted writes were lost. Which the clients, attempting to perform those writes were never told they succeeded, so they are now told that they failed. They will need to retry, and this is how we keep the system in a good state. The follower who used to be the leader now becomes a follower. It now catches up from the existing leader of what the correct state is. Same as for the other leader on the other follower on the other side of the partition. And thank you. All right, so now we have a partial network partition, and in this case, one leader and the leader and 1 follower can't talk to each other in this 3-leader system or 3-node system, but 1 follower on the bridge can actually talk to both. So what happens? The follower that can't talk to the leader thinks the leader is dead and starts a new election. However, the follower that can on the bridge that can see the leader is still alive says, rejects the election because it can still see the leader. Leader's not dead. However, the leader missed the election, and based on how the protocol works, which I'm hand waving over, the leader has now missed important information. It needed to do something to participate in this election that it didn't do, and so now it's out of date. And because it's out of date, the follower can receive on the bridge follower no longer accepts its updates because the leader is now out of date. The leader is then resigning. So now the follower can call a new election since the leader is resigned. And if we're unlucky, the same leader gets reelected again. And now we're back in the same state we were before. And the same follower that couldn't connect to the leader still can't connect to the leader, still calls a new election. And we're just left in this endless cycle until either the network partition is healed or the follower that can see both on the bridge gets elected as the leader, because then things can continue on. Both followers can see the leader. Everybody's happy and is good to go. So this actually happened, and actually happened pretty recently on November 2nd in Cloudflare. So a failed switch created a network partition in a 3-node etcd cluster, and etcd relies on Raft for consensus, a modified version, an optimized version to Raft. So what ended up happening is what I just showed you. The side 2 follower repeatedly initiated leader elections and voted for itself, while the bridge node repeatedly voted for the side 1 leader, which you could still connect to. And so that meant that the leader kept getting reelected, the follower that was disconnected from it kept calling elections, and the entire cluster came to a dead halt because no operations can be performed during leader elections, which were happening endlessly and continuously. Finally, so this happened for 6 minutes, and then finally the network partition was fixed. But this turned out to be too long. Cloudflare systems needed to access the etcd cluster to figure out where their primary database is. Because the cluster was dead, they created a new one, and then a bunch of replicas got rebuilt on that new cluster. So basically, while the issue was only available or only an issue for 6 minutes, it was 6 or 6.5 hours later that Cloudflare's control plane was offline, or at least degraded because of this 1 6-minute outage. All right, I'll pause for more questions. Thank you for filling in my hand waving a little. I appreciate it. All right, no further questions, so I'll move on into an analysis of network partitioning failures in cloud systems. Now, 3 of the 4 authors here, this is actually the predecessor paper, the one we're discussing, or I'm diving into more tonight. So I ended up coming across this during research. As I said, I read the Partial Network Partition paper as part of class, and then doing research for this presentation, I found its predecessor. So before studying the effects of partial network partitions, Ahmed, Mohammed, and Samer studied the effects of all network partitions. And as it turns out, a lot of these systems are bad at complete network partitions too. So for the purpose of the study, 136 different failures were studied, mostly from public issue tracking systems, but also JESPIN reports. And also they built their own fault injection framework called NEAT. And they found 32 additional failures or issues as a result of their own fault injection network fault injection system. So we'll dig into findings. There are 13 in all. As I said, this is not the paper we're studying, so I'll be doing a lot of skimming over, and we'll go through it kind of quickly. But first of all, a large percentage, or 80% of the studied failures, have had a catastrophic impact, and most commonly data loss. And catastrophic impact for them, they define as if the system can no longer meet the guarantees it promises. So if it promises to store your data and you lose data, that's a catastrophic error. If you're reading old data and it promises you'll always read new good data, that's a catastrophic error. Same thing, if you're a locking system, you break locks, the system won't crash, the data will always be available. If you deleted data, it won't reappear. All of these things have shown that if you have either a full or partial network partition, you can see these kinds of issues occur. In addition to that, the failures themselves are more often than not silent, and which means you never knew anything was wrong with the system to begin with. And also that even when there are errors, it's hard to know what to do next. So one example they provided was REAC. If a client tries to replicate a value towards a quorum of nodes and is unable to, the client gets back an error saying the operation has updated a subset of replicas, but not all of them, which is unhelpful for the client to figure out what to do next. So which nodes do I need to replicate to? Do I retry the operation? like the error message isn't really helpful as to what the client is supposed to do in the situation, and more importantly, it might even be possible for the cluster to fix itself once the partition is healed. The next finding is that 21% of failures lead to permanent damage to the system. And this permanent damage persists even after the network partition heals. So in one case, in some systems, if a new node is unable to reach the other nodes as it joins the network, it assumes the entire network is dead and it is the sole survivor, and it creates itself a new independent cluster. And then even after the network partition is healed and the two clusters can talk to each other, the new cluster doesn't realize that, oh, there was a mistake. I actually should join the other cluster. These two clusters, remain independent of each other. And so clients connecting to these two clusters will end up, making your data even more inconsistent than before. All right, so next up we have leader election, configuration change, request routing, and data consolidation are the most vulnerable systems to network partitioning. And so you can see this chart about how they break down. What this means is that leader election doesn't work correctly if there's a network partition. Configuration change of different kinds doesn't work correctly if there's a network partition, and so on and so forth down the line. So these are things that you need to worry about during network partitions. Another issue that they came up with was 64% of the failures either do not require any client access or require client access to only one side of the network partition. So for example, if you end up isolating the leader, that leader may end up responding to requests even though its data is out of date, and even though it knows it's no longer connected to its followers. So this could lead to stale and dirty reads where the leader has different information than the rest of the network does. So next up we have, while the majority of the failures requires a complete partition, 29% of them caused by partial partitions. We will dig into this. One note about this table: a simplex partition is where traffic only flows one way across a divide. So if you have A and B and there's a partial network partition, A can still send messages to B, but B can't respond back to A. So a majority of the failures triggered by a network partition require 3 or fewer input events to manifest. This is, of course, concerning because it means that your cluster can go bad in a really fast after your network partition. And you can dig into things that can happen in order to trigger these. In primary cases, either it takes a write request and a read request, or you can acquire a lock. Most commonly, it's your network partitions, and then you issue a write, and then now your system's out of date because half of your system is saying one thing, and the other half of your system is saying the other thing. All right, so next on, all the failures that involve multiple events only manifest if the events happen in a specific order. So that means that you only have to check a few different things in order to confirm that your system does the right thing. So in the vast majority of cases, the network partition is first, and then after that, order is not important, or there's a natural order. Natural order meaning these are operations you would expect to perform if you were testing this yourself. Like if I want to lock a lock, odds are at some point I want to unlock that lock. Or if I at some point want to perform a write, odds are after that write, I want to perform a read to either see the aggregate results or confirm my write has persisted. These are things that you expect to happen. And if you follow these specific order of events, your network gets into a bad state if a network partition came first. All right, the majority of the failures manifest by isolating a single node, and 45% manifest by isolating any replica. So in 45% of cases, it doesn't matter which node you partition, you're going to start running into trouble, or your distributed system is no longer going to work correctly, start distributing catastrophic failures. On top of that, but however, in other cases, in 55% of cases, it's actually a very specific node that has to be partitioned. So if you partition the leader from the rest of the network, 36% of the errors or issues came from there, or a central service, which is such as a Zookeeper cluster or HBase master. And then if you partition a node with a special role, such as the MongoDB arbiter, you can also get into a bad state for your cluster. Number 10, the majority or 80% of the failures are either deterministic or have known timing mechanisms, which means either there are no timing constraints at all in 62% of cases, or you have a very specific timing, a very specific time window where something is if the wrong event happens in that time window, your cluster gets into a bad state. So for example, if a write is issued before the old leader steps down, that write will go to the old leader, the write will be persisted by the old leader, and that write is effectively lost. Number 11, the resolution of 47% of the failures required redesigning a system mechanism. And redesigning a system mechanism, for example, is implementing a new leader election protocol on MongoDB, or changing the how configuration changes happen in Elasticsearch. And as you can see, these also wind out to be a long resolution time. If there's a design issue, which is almost half of the cases, it takes almost 7 months to solve the problem. And then for an implementation, it takes almost 3 months. Moving on, all failures can be reproduced on a cluster of 5 nodes, with 80% of the failures being reproducible with only 3 nodes. That means it doesn't take a lot to verify these things are working, which is good. That means that you don't have to spin up 80 nodes in your AWS cluster and pay them a bunch of money. You can do it pretty quickly and possibly even on your own machine. And number 13, which is our last one for today, or for this paper, the majority of failures can be reproduced through tests using a fault injection mechanism. And as posted in the chat, we have the authors have provided Neat. So if you want to learn more about that, we have the source code and we have the paper. All right, I will pause for questions. Thank you, David, by the way, for doing all the background research as we've been going through. Yes, or they just don't get fixed 20% of the time. I assume that means they haven't been fixed yet, but we will see as time progresses. All right, no new questions. Then we'll move on. So going back to the original slide of partial network partitions, we have side 1, side 2, and the bridge. So just as a reminder, so this paper also dives down specifically. So now we're on our actual paper, the one that I promised I would present. We're actually there now. We made it. So now we're going to dig into 51 partial network partition failures across 12 cloud systems. Again, most of these were pulled from the issue trackers, or all of them were pulled from public issue trackers. Also to note that a lot of these actually already have partial network partitioning support in them, and we will dig into later on what this support looks like and how and its pros and its shortcomings. So their first finding in digging into these failures is that a significant percentage, or nearly 75%, of the studied failures have a catastrophic impact. Catastrophic, again, we promised the cluster was going to do something, and thanks to a network partition, it no longer does that thing. So you can lose data, your system becomes unavailable, there's a stale read, your data becomes corrupt, you get a dirty read, your data becomes unavailable, and then also reduced availability is tied for data loss as one of the most common impacts. Next up, we have most of the studied failures are silent. Again, a little better, I think 90% in the other paper, so a little better with partial network partitions, but not great. So the user is still not informed about their occurrence. And even when we have rare warnings, again, they're also quite ambiguous. In Elasticsearch, if a client sends a request to a replica that is partially isolated from the other replicas, the replica will return a rejected execution exception. What is a rejected execution exception? How should the client handle a rejected execution exception? What is a rejected execution exception? You really have to be well-versed in Elasticsearch to know how to handle these situations, and that's unfortunate for what it is. So leader election, configuration change, and replication protocol are the mechanisms most vulnerable to partial network partitioning. So this is a subset of the issues from all network partitions in the previous paper, but leader election again comes out on top as one of the mechanisms most affected by a partial network partition, and configuration change being second, and the replication protocol being third. Most failures do not require client access or require only that clients access one side of the partition. Same finding as last time. Now, that said, some systems do limit access to one side of the partition to reduce impact, and we will dig into that in later slides. The majority of the failures require 3 or fewer events. Again, we saw this before. Other than the partial partition to manifest, again, same things as before. You worry about reads and writes or writes before the old leader stepped down. All of those issues manifest. All the studied failures can be triggered by a single node partial partition, where a third of them happen by partitioning any node. So a single node partial partition, one node is on one side of the partition, and all the other nodes are on either the other side or bridge nodes. Bridge nodes being nodes that can still talk to the entire network. So you can partition any node that's one third of the issues. If you partition specifically the leader, that's 45% of the issues. And then nodes with a special role and special central service. We talked about that with the last paper. That we're talking about Zookeeper, the MongoDB processes, things that have very special roles in the cluster. If you partition them, your cluster gets into a bad state. When all the studied failures, except one, are deterministic or known time constraints. So only one of these issues is non-deterministic. It requires interleaving multiple threads. The rest you can test out on your own machine at home, and you'll see that either no timing constraints are needed or there are known timing constraints. And we talked about this in the previous paper. This is like, for example, if a write occurs before the leader steps down. The resolution of 57% of the failures required changing the design of a protocol or a mechanism. And again, now it's even worse for partial network failures or partial network partitions. Design issues now took more than 7 months, right? 8 times 3 is 24. Yeah, more than 8 months, less than 9 months to resolve. Implementation issues now take more than 3 months to resolve. And again, there are still 25% of the issues still remain unresolved. All failures can be reproduced within 5 nodes, and all but one can be reproduced using a fault injection tool, such as Neat. So 3 nodes, again, you can see that over 3/4 of the issues you can reproduce with 3 nodes, and all the issues can be reproduced with 5. All right, coming back to this. So one more example. We have one example, which is a partial network failure, which is actually true for ActiveMQ, Kafka, and Mesos. All suffer from this exact situation. All 3 of these clusters rely on Zookeeper for leader election. So if you have a situation where your replicas are on one side of the data center, your leader is in a different side of a data center, and there's a full network partition isolating the leader, what happens is the replicas recognize their leader died. The leader, as far as it's concerned, all their followers died. Zookeeper can't connect to the leader, so it says, all right, we need to elect a new leader of the existing replicas. Great. This is a good thing. This is how it's supposed to work. However, when you get with a partial network failure or partial network partition, you end up with a full cluster outage. Now, why? Well, again, we have the same 2 issues again. The replica says, our leader died. The leader says, my followers died. But Zookeeper is all on the bridge nodes, so Zookeeper thinks everything's great. It can connect to the leader, it can connect to the replicas. As far as it's concerned, everything's fine. And now your system can't process any requests because the leader is supposed to process writes, but it can't reach quorum. The readers can't process reads because it doesn't know if it has the most recent data, and your cluster's gone. So I'll pause for questions. No new questions thus far. So cool. Then we'll go into the modern fault tolerance techniques. Which is a study of the patches that were actually used to fix these network partition issues in the systems that were studied. And we start with identifying the surviving clique. So we identify the largest clique of the fully connected nodes, and we shut down the rest. This means, if you can see from the diagram, in 1, 2, 3, and 4 nodes are all accessible to each other. 1, 5, and 6 are all accessible to each other. Because 1, 2, and 3, and 4 are all fully connected and at a larger group than 5 and 6, we shut down 5 and 6. So this sounds great in principle. However, VoltDB shards data and then makes different nodes responsible for different shards. So, and backup, both primary and backup. So if you get into a place where the primary is on 5 and the secondary is on 6, then you've lost access to that shard. And in that situation, VoltDB shuts down completely. Now, what the authors of the paper found that it actually only takes about 20% of the nodes to lead to a 90% probability of cluster shutdown, which is unfortunate. Also, with the situation, you are also shutting off half your cluster, which means you're no longer as capable of responding to reader requests. Your load balancing is not as strong as it used to be, and you can run into trouble that way as well. The next situation or the next solution is checking neighbors' views. This is implemented by RabbitMQ and Elasticsearch in different ways. We'll talk about RabbitMQ first. RabbitMQ on a lost connection will broadcast to the network to determine if the partition is either partial or complete. So can anyone else reach the node? If so, great. Or if so, then it's a partial partition. And if not, then it's a full partition. Now, there are two different rules. There are really three different rules, but one more like 1, 2, and 2A. The first one is if there is a partial partition, and I'm partially partitioned from the network, I disconnect from all the nodes that can see the node I'm looking for. And this is effective to escalating to a complete partition. Now, this doesn't shut off the nodes. It just causes both sides to work separately. And that means that if some clients are writing to some nodes in the cluster and other clients are writing to other nodes in the cluster, then you have effectively data loss. Your clients reading from one side won't see writes happening to the other side and vice versa until the partition is healed. The other option that you can sign up for is pausing. And so that means that if there is a partial partition, I can pause my operations. And that means that the rest of the cluster can continue on and continue on normally. Now, this is generally a better state to be in. However, you have to be careful if there's only one bridge node, which means there's exactly one node in the cluster that can see all the other nodes. Almost the entire cluster pauses because all the other clusters recognize around the same time, I've lost access to the rest of the network. It asks around, it's this one bridge node says, yes, I can respond to everyone. And now you're effectively maybe just that node or maybe that node and a couple other surviving nodes shut down based on order of operations. And then basically you're down to effectively nothing. You can't perform any writes anymore because you can't reach quorum. There's also a policy to pause if there are designated anchor nodes cannot be reached. So this is kind of an interesting one. You can designate in RabbitMQ some nodes to be anchor nodes, and these are nodes that you always expect to be up, and you never expect to have a network partition between them. So however you decide to have magically set up your network such that either these nodes will always be available and always be connected to each other, then you can say to other nodes in the system, all right, if you can't access these nodes, pause operations. And so these anchor nodes then become, contain quorum, and so your cluster can continue on. This is, of course, incredibly dangerous because you're making a promise that these anchor nodes will never be partially partitioned or fully partitioned between each other. And so if that happens, you get into some really weird states with RabbitMQ. So it's a safer option if you can complete the guarantees and a much more dangerous option if you can't. All right, so that's RabbitMQ. Now we'll talk about the Elasticsearch implementation. So on a lost connection deleter, we broadcast to the network and determine if the partition is partial or complete. Again, same as before. If it's a partial network partition, we're going to pause operations. If it's a full one, we're going to elect a new leader. Again, this is focused on the fact that Elasticsearch has a leader and a bunch of followers. In our case, masters and replicas in their terminology. So that means that if all nodes that can't reach the leader must pause. So again, if we're back to a case where only one node in the cluster is a bridge node, that means that all the replicas will find out from that one bridge replica that yes, the network it's only a partial partition. I'll shut down, and now the leader can't reach quorum anymore because there are only two nodes, which effectively shuts off the entire network. There we go. And then so now 4 out of 5, 3 out of 4 are either way, our next one is failure verification. And we've actually seen this already. So if the leader is announced as failed by one of the other replicas, verify yourself that the leader is unreachable before participating in a new election. This is used by both MongoDB and LogHabin being the original Raft implementation. We actually saw this. We saw what happens when there's a partial network partition and a leader and a follower cannot talk to each other anymore, and it just ends into an endless cycle of re-elections. And that happens to MongoDB as well, and that's just not great. we didn't solve anything. On top of that, the mechanism can't be generalized, as no generic framework can ignore all failures. So it really is implementation specific to what your distributed system is doing. And our final one is neutralizing partition nodes. So nodes may update a shared state from opposite sides of a partition. So, for example, there's some some node that's contains a database, and then both sides of the partition are updating that database. You might end up into either a data loss or inconsistent state. So, if that's possible, you want to be able to neutralize one side of it so that they don't perform any of these operations. These are all independent implementations created by HBase, Hadoop, MapReduce, and Mesos. HBase renames shard directories in HDFS. That means that if you're on two sides of the partition, now you're writing to different files. One of these files is going to get lost, depending on which one wins at the end. Hadoop restarts jobs on the other nodes. So this is the MapReduce version. Will restart jobs on other nodes. It uses a completion network in that shared state for synchronization. And this way, if these two operations are being replicated on opposite sides, they don't all write to the same place at the same time, or at least only the winner does. So there's going to be a winner and a loser. And even though there's a loser that does a bunch of extra work, they know not to write the results. And then finally, Apache Mesos, the leader reschedules tasks and the followers pause their operations. So the leader is going to reschedule tasks to the nodes it can find, and any followers, if it loses access to the leader, says, all right, my work's been reassigned. I need to stop doing whatever I'm doing now. Now, unfortunately, this is not practical for system-wide fault tolerance, and it leaves existing nodes idle, reducing performance and availability. So we now have a summary of shortcomings. You may look at this table and immediately say, maybe I shouldn't use RabbitMQ. I'm a production user of RabbitMQ. I'm not completely going to disagree with you on that one. But the other thing to take away from this table is network partitions are hard to solve for, and a lot of different systems have taken a lot of different stabs at it, and partial network partitions are hard and are still have shortcomings. So their solutions haven't quite made it. And then you look over and you see, wait a minute, what's this Nifty thing? It seems to have solved all my problems. So let's find out. So Nifty is presented by the authors of the paper. They describe it as a transparent communication layer that masks partial network partitions. And Nifty builds an overlay between nodes to detour packets around partial partitions. What does that mean? So we're back here again. We've seen this slide. I think it's the fourth time, if not the third. If not, it's at least the third time I've shown the slide to you. We have a partial network partition in place, and we note that one side is the bridge, and this bridge is the it can talk to all the nodes. But bridge is an odd terminology for it. Why did we call it a bridge? Oh, because we can reroute all our packets through it, bridging it across the partial partition to the rest of the network. That's sensible terminology. Pat yourself on the back if you saw that coming. And then again, yellow can do the same. Yellow can route its packets through the bridge as well. Green can route its packets to the bridge, and now we have a full network connectivity, even if we're now increasing load on the bridge side of the network. All right, so we'll talk a bit about the overview. I'll pause for questions. I don't see any new questions, so I'll proceed on. So with Nifty, every node in the cluster runs a Nifty peer process. This is independent of the distributed system that you're running. You don't need to modify your RabbitMQ implementation or your HBase implementation or your MongoDB implementation. This is a peer process that's basically managing your routing tables in your network or on the machines that they're running it's running on. And so Nifty also provides an API for these applications to actually recognize these partitions and handle them. This may mean rerouting traffic. It may mean degrading availability based on based on which nodes or which node is on which side of the partition. And this will allow the cluster to continue on without overloading the bridge nodes. So it does this There are a few different pieces. We will start with connectivity monitoring. So the Nifty processes talk to each other through heartbeat monitoring. They track distance vectors to each node from where they are to how they get to somewhere else. Hopefully, in a fully connected network, the distance is 1. You can send a packet to any node of the network. However, if there are 3 missed updates, 3 missed heartbeats, a connection gets lost. And we'll talk about how, in the next slide, how we recover from that loss. In the meantime, even if the connection is lost, the Nifty processes will still attempt to connect to each other. So this way they can detect once the network partition is healed and recover automatically. In the paper itself, the implementation uses one UDP packet heartbeat every 200 milliseconds. And so that means in a 9-node system, there are only 40 packets sent every minute, which you'll see as we get to the results doesn't have a strong impact on the overall performance of these distributed systems. All right, so we'll talk into recovery next. Each process sends distance vectors, so it sends these distance vectors to each other. These are piggybacked on the heartbeat messages that are already being sent out. And then all these processes can build routing tables for themselves based on others to figure out, okay, who can see whom, how far away is everybody to each other. When a connection to a node is lost, we find a new route to the node. This uses the Bellman-Ford distance vector routing protocol. I've outlined it on the right-hand side, but if you wanted to think about what a routing protocol would look like to figure out how to reroute in the event of a partial partition, you'd probably come up with what this is. Ultimately, you're using link weights to figure out what the shortest distance is based on the weight to send packets, minimizing your network load, and then you just keep track of those as nodes come online, nodes go offline, partitions occur, partitions disappear, and then you build routing tables as these events happen. These routing tables can contain the destination IP address of, so if I want to send something to somewhere, if destination IP address, how many jumps in the network or hops it'll take to get to the network to get there, and then the MAC address that I want to send it to, which is the next MAC address in the chain. So from this diagram here, we have a 4-node cluster. There are partial partitions that prevent 1 from talking to 4, 2 from talking to 4, and 3 from talking to 1. And so if 1 wants to send a message to 4, it has to route it from 1 to 2 to 3, and then finally to 4. So what happens is 1 checks its network, its routing table. It sees that if I want to send a message to the IP4, meaning the 4th node, it's 3 hops away, and I need to send the message to the second MAC address for the second node. Once the node receives that, once node 2 receives that message, it looks in its routing table, it sees that 4 is 2 hops away, and the next message needs to go to MAC address for the 3rd node, sends the packet back out again. 3, as you can imagine, says, oh, you're 1 hop away, I just send it to your MAC address, puts the packet back on the wire, and it finally reaches its destination. Now, how this happens is Nifty uses the OpenFlow and OpenVSwitch APIs to deploy these routes. And as I said, once it receives the packet that doesn't go to it, it goes through its routing table and figures out how to send it across the network so it gets to the right place. So node classification, we're talking about the API now. Clusters can use Nifty to avoid excess traffic through bridge nodes. So you can find out from Nifty which nodes are on one side of the partition, which nodes are on the other side of the partition, and which nodes are the bridge nodes that connect them. Now, clusters can use this information to either move the processes that it needs to bridge nodes or just degrade functionality, just to avoid overloading the bridge nodes. And we'll get into a case example soon. Thank you, David. It's actually all-to-all routing. Just reading the question. The question was, is this a sort of a gossipy heartbeats? And not gossipy, it's actually all-to-all. It is an interesting, I am curious if a gossip heartbeats would make more sense. But it could have just been that the authors decided to do the easiest one, which would be the all-to-all heartbeats. All right, moving on to the evaluation of these ideas. So the evaluation seeks to answer 3 questions. 1, how much overhead does Nifty impose when there are no partitions? What is a system's performance when Nifty is under a network partition? And then what is the utility of Nifty's classification API, which is the API that the services that your distributed system can call to find out your network topology? You can look at the test bed. Most interestingly, to remember is that you're going to see data based on 30 runs. So you're going to see the average of 30 runs with a less than 5% standard deviation. And rather than actually chop wires or start ripping out nodes, OpenVSwitch drops packets between nodes to simulate a partial network partition. All right, so HDFS actually sees the most degraded performance. As you can imagine, if you're sending a lot of data through your HDFS network, you're going to see a lot of degraded performance during a partial network partition. But if Nifty is running with alongside HDFS, it's actually about the same performance, and we'll dig into actual numbers at the end. So these are this is 6 nodes, 1 name node, 5 data nodes. If you're not familiar with HDFS architecture, your name node is effectively your leader, and it contains the network, basically the topology of where all your data lives. So which nodes contain which data is all known by the name node. When any client comes in and asks the name node, I want this piece of data, where do I go get it? The name node says, all right, talk to node number 3 or talk to node number 4, or trying to do some load balancing across your different replicas to get the right data. All right, moving on to Kafka. Kafka, you can see, has a severe performance degradation when there's a partial network partition, and if you put Nifty at it, there's still some performance degradation, but not nearly as much. One thing I should also note before we move on, if you don't see an option that says like HDFS-P means the version with the partition. So you can see with Kafka, you've got Kafka with Nifty running alongside of it. That's the black line. The red line is Kafka with Nifty running alongside it with a partial network partition. And then finally, the gray line is Kafka with a partial network partition. And you can see how those performance changes between those 4 different options. On the left side, you have straight HDFS with Nifty running alongside it, and then HDFS with Nifty running alongside it with a partial network partition. There is no HDFS with a partial network partition because HDFS fails. HDFS unfortunately ends up with a full cluster shutdown, which is why you can't actually compare it, because there's no running cluster. And we'll get into that at the end. Moving on to MongoDB. MongoDB, again, full cluster shutdown when there's a partition, but it doesn't really matter if there's MongoDB or with Nifty, without Nifty, and even Nifty with a partial network partition still chugs along just fine. ActiveMQ, you can see the same. Again, ActiveMQ will completely shut down if there's a partial network partition. We actually talked about that a little bit before. And then with the partial network partition, everything continues on just fine. VoltDB, this is a straight VoltDB. We'll talk about some mechanisms later about how they've changed it to use the classification API. But this is straight VoltDB with just either itself with Nifty and with Nifty with a network partition, or partial network partition. You'll see everything continues on just fine. And even the tail latency, which is 99th percentile, again, can hardly tell the difference. And you can largely see the same thing for RabbitMQ. RabbitMQ is also one of the few nodes or a few systems that can handle a partial network partition, even if it has an immediate decrease in throughput if it occurs. And then same thing for tail latency. And again, if you have Nifty running with a partial network partition, everything seems to be just fine. There is a little bit more overhead in this particular case when you have Nifty running alongside RabbitMQ. But overall, when you take a look at how partial network partitions happen, it's not as bad as it looks, or it's not that bad. Sorry, I'll pause here. Some questions. All right, so the question was, is the use of the Bellman-Ford presuming uniform link times for each hop? Yes, it is. Unless there's more information provided, or at least Nifty as designed on this test bed assumes that everything is connected, effectively the same cost at anywhere in the network. So hopefully that answers your question. And feel free to post back if I didn't. All right, so classification API for VoltDB. So let's see here. In VoltDB, all multi-shard operations are processed by a single server. So I mentioned before, VoltDB will split your data into multiple shards and then farm out shards into different nodes in the cluster. If you ask for data across multiple shards, there needs to be a process somewhere that's going to receive that request, split it out into read requests to the various shards, and then forward those read requests out to the different nodes in the cluster. Now, if you can imagine, now VoltDB, this isn't an issue when there's a partial network partition on straight VoltDB because VoltDB dies. But if you're now in adding Nifty to it, now you have run the risk of having a lot of data run through the bridge nodes in the network. So VoltDB, so you can use VoltDB, and how the authors use it here is if this happens, VoltDB will move the multi-data partition initiator, or the MPI, out to one of the bridge nodes, which has access to the rest of the network. So this way, you don't have to worry about a lot of extra data getting sent through the bridge nodes because they're originating from the bridge nodes. And that shows, and that ends up with an 11% decrease in the latency from the VoltDB we saw before to this improved version of VoltDB by moving the MPI processes to the bridge. And also, once you add this, you're within 4% of the performance without a partition. So, which means that VoltDB with Nifty, with the classification API, is 96% as performant as VoltDB with no network partition, which is great news. So overall, final results. So one thing they also went through is they tried to scale out as far as they could, and they did notice that once you get out to 100 different nodes, your performance starts degrading by 3.5%. There's just too many messages going through the network at that point. So that means that this will not scale to thousands of nodes in the cluster. That means that this won't really work for large clusters, but it will work very well for small clusters. And they're currently exploring a fault tolerance technique for larger clusters, which is probably why this paper is called Toward a General Fault Tolerance Technique and not a General Fault Tolerance Technique. I mentioned before that all these systems shut down under a partial network partition without Nifty. So HDFS, ActiveMQ, MongoDB, and VoltDB all suffer a complete cluster pause or shutdown. RabbitMQ or Kafka end up either doing that or they reduce system throughput by 50% in handling the partial network partition. Of course, they also found that Nifty effectively masks this partition, or the partial network partition. So the HDFS system throughput is reduced by 45%. I showed you that chart before. As traffic is redirected through the bridge nodes. For the other 5 systems, you see throughput decrease between 2 and 7%. Not that big of a deal. Latency increases by 3 to 8%. Also, not that big of a deal. And then we also saw that if you're already using Nifty on VoltDB and you throw in the classification API, even that decreases by 11% latency and 4% increase in throughput. And if you want the source code, there's the link. So that takes us to the end. I will bring myself back on the screen. Let's see how this works out. Oh, I did that wrong. There we go. So I'm happy to answer more questions. So what's stopping services from implementing this directly in their applications? Compiling the C++ code and running it, as far as I know. Are these just sort of lower level networking APIs that most user apps won't use? As far as I can tell, yes. I am definitely not aware with the OpenFlow and shoot, now I actually got to go look. Hold on, let me disappear and go find the right slides. OpenFlow and Open vSwitch. Yeah, I've never heard of these before this paper, so I assume these are not things that you would expect to find in the actual or in everyday use. I'm guessing layering would be a good idea to reduce application complexity. Yeah, that's also true. I have all the papers printed out in front of me. So if you have more questions, I'm happy to dig through the papers and find the answers for you. All right, then it sounds like we're, yes, so many papers. All right, then I think that'll do it. I'll stop streaming now. Thanks, everyone. It was a lot of fun.